Yeah, I had no idea. Getting old. All right. Okay, so let's do asymptotic analysis. So, why do we even need this, right? It just seems like more math, more rigorous stuff on top of what we're already learning in this class to begin with. Well, as we know, we need to sort of measure the efficiency, the speed of our algorithms, right? What if we're making an algorithm or like say a method in a class that just takes a long time to run? Maybe we have a runtime error, for example, in Java, or maybe say we're doing something, spending way too long to do a problem, we can just cut the problem in half. Maybe we don't even need to cut the problem in half. Maybe we just need to get like one element. Maybe our method actually takes a constant amount of time to do this exact same thing that we're intending to do. Asymptotic analysis lets us like sort of envision our method such that if my input size is say really, really large, so say I'm inputting like a list, a linked list that's like maybe like a bajillion lengths long, right? If I wanted to scan this, we would say, all right, well, if I'm going one by one by one, I know that the runtime for this would just be linear time, right? But what if I have to do a lot of work per node before I go to the end of the linked list till I hit my null pointer? That's when things get a little more convoluted. And that's why we need to investigate how much work are we actually doing before we go from start to finish in terms of n, the input size. Right. Okay. Some jargon. I know this sort of confuses a lot of students when they first see it. There's a lot of notation that comes with this. We aren't going to go too heavy in the notation because I believe it gets in the way of actually solving these problems on like the sort of level that's necessary to solve these on an exam or on a homework set, for example. But just as a refresher, when I say something is a big O, that essentially means that I've created a sort of an upper bound for how my function will perform. So say I gave you the example of the linked list, right? Draw some right here. If I wanted to traverse this linked list from start to finish. You can say, oh, my bad. Oh, so the zoom. Okay. That what? What? Sorry, my bad. Try sharing your screen again on your iPad. Sharing screen on iPad. Oh, it's working.
You just need to make sure, like, on your end, like, like, where exactly, like.
Maybe try stop sharing your screen for the slides for a little, and then.
Okay. I see the difference. Okay, so I guess I'll just do that back and forth. So say I have this linked list here, right? And I start with the first element, and I know I want to go node by node by node until I've reached my null pointer. We would say, right, this is a linear time algorithm, simply just scanning the linked list. But if I were to say the upper bound for this sort of algorithm is O of n squared, that would still be an answer. But it's not a really good answer because although I know it just takes linear time to scan this, when I say O of n squared, that simply means that on the worst case, this method can take, not the worst case, my bad. The most time that this method could take is no worse than n squared. So here we have the, say y equals to n linear, and I have the parabolic function here, so y equals n squared. Just by this diagram alone, if I know that this line here is the true runtime of my algorithm, and I say, oh, well, why don't I just write O of n squared? That tells me I know that I'm not going to do worse than this parabolic line. That is correct because it's below the parabolic line. But see how it's not really any good? It's not like a good estimate. It doesn't tell me the true nature of how my method is behaving in the long term. So therefore, I would rather say the function runs in theta of n. I know I'm going to scan all the elements, and that is the time that it'll take to go from start to finish. Okay, let's see. We'll start this again. Okay. So let's move on to the next slide. We have some asymptotic bounds here. If you see in the left, bottom left region of our XY axis here, we see that it kind of shows you how the polynomials and the logarithmic functions start as you begin, right? For small input size, say I have an input size of 2 or 3, you don't really get a gist of how the function behaves in the long term, right? So when I say I'm doing asymptotic analysis, I'm saying I'm going to the far right-hand side of my x-axis. I want to see what happens when the input is really large. Resume. Apologies.
Here, try to share your intelligence.
Okay. Okay. Yeah, again, if you see on the left-hand side of our bottom left-hand side of our XY axis, we see that it doesn't really tell us the big picture of how our polynomials behave, right? We need to look at the far right-hand side of how they behave on the long term, in the long run. So as you see, like 2 to the n, say I have an input size of n equals 3. 2 to the n would be 2 to the 3, which is equal to 8, right? What about n squared? If n equals 3, again, for n squared, that is 2, n equals 3, sorry, blanking out. That's 9, right? We know 8 is less than 9, so that would make me believe, all right, well, why don't I just pick 2 to the nth power as what I want to say this method runs in? It's obviously less, right? I prefer that. But if you look at the long term of this of these two functions, you'd see that 2 to the nth power dominates n squared. We'd rather prefer it n squared runtime algorithm. Any questions on that so far? Okay, let's see. I think now we could do like an actual problem. Okay, so let's see. We'll do this problem, and I'll have you guys do the next one. It'll lead up to it. But so say I have this method vampire, right? We're assuming n is really large. So as I get to this first for loop, I equals starts at 1, right? I traverse from I all the way to n. All right. What does the inner for loop look like? It looks like in the for loop, when I see this, I see some sort of dependency. J has a dependency on I, and I was defined in the previous for loop. That's probably one of the first things you want to notice. And you don't want to just immediately, like, what I'm doing, like line by line by line, immediately know what's happening. That's not really the case for solving these, but you do want to at least scan the method, get a gist of what's happening. So as a matter of fact, I'll let you guys sort of look at this for a moment, and I'll take some answers of what you guys think it is. So I'll give you guys like a minute or two. I'm sorry. Working on this problem right now. All right, so let's begin. Let's see, I will stop sharing on this here. Just see, is it transferring to the iPad? No.
Press share. To share. And then press, yeah, just stop sharing. And then.
Okay. All right.
I think that's precise.
All right. Okay, so we're assuming like a big input size of n, right? So what happens first? First, I'm traversing to the outer for loop. I equals 1. I go into the inner for loop now. How many times am I going to activate this inner for loop for the first I index, right? We know that there's this dependency, right? J is less than I. So as long as J is less than I, or we could even say less than or equal to I, we know that we're going to do some amount of work right here, right? We're going to do print something out. We can say that this is constant work, call it 1 unit. So I have here, I equals 0, J equals 0. So that means I'm putting 1 unit of work for this traversal. The next time I go to the outer for loop again, now I equals 2 because I'm increasing by 1, right? So I'm in this portion here. How many times is the inner for loop going to run? As long as J is less than or equal to I. So I'm printing once. I'm printing a second time. All right, now I don't satisfy this J less than or equal to I anymore. All right, how about the next one? When I equals to 2, that means I can go from J equals to 0 all the way up to J equals to 2. So now I have 0, 1, 2. And I'll do one last one. In the case when our for loop is I equals to 3, the inner for loop is going to do, it's going to go from J equals to 0, J equals to 1, J equals to 2, J equals to 3. How many units of work am I doing now in this case? It's going to be just 1 more. And we can see like a pattern starting to form here, right? Every time we enter this inner for loop, we're increasing the amount of work by 1 unit, okay? With asymptotic analysis, we need to do the step-by-step sort of look into the method in this specific case because, right, we're trying to find out how much work is my method going to be doing from start to finish. At the start here, I am doing 1 unit of work. So this guy. At this inner for loop, I'm doing 2 units of work. 1, 2. 3 units of work. 4 units of work. Does anyone know how many units of work I'll be doing at the final run of this inner for loop? N plus 1? About that, right? Like we don't know if it's like 0 indexed or if we count the 0 at the first line, but we know it's like around n, right? So we can say at I equals to n, we know that we're going to be doing about n work for the inner for loop, right? So we have all of these n's, and I'm not going to count them all, but we know that this last number is n work. This first one here was 1 unit of work, 2 units of work, 3 units of work, and so on, right? Asymptotic analysis, I want to find the sum of this. What's the total sum of all this work? The first one, the second one, and so on. I can generalize until I get to the last one of n, right? And here, this is what we would call an arithmetic sum. An arithmetic sum in this case, we see that every single portion here increases by the same exact size. So plus 1, plus 1, plus 1, plus 1. We have an arithmetic sum. When we know we have this, we say that the sum is essentially going to be the last term squared. So I'd say my function runs in theta of n squared.
It's something that if it's an arithmetic sum, it's always going to be square or the last.
Exactly.
Like,
Yeah, you can think of it as a rule because say, for example, I have a different arithmetic sum, like say, for example, each work in this, right, in each iteration, say I had, again, say 2 plus 4. We can even do this actually. 1 plus 2 plus 3 plus 4. But say our last term wasn't n. Say we know at the final for loop, the work done is n squared. Right? If this was the case, again, we see that if we look at the first elements, we have an arithmetic sum. We can generalize, say, okay, I know the last term is going to be n squared. Like I said earlier, the sum would be the last term, which is n squared, squared. The last term squared would then just be n to the fourth power. So this is how you can approach these sort of problems once you've found out all the work.
Just want to add on, if you calculate the sum of this sequence, you can do I forgot what it was called, but you can do n squared plus 1, and n squared minus 1 plus 2, or n squared minus 2 plus 3, dot, dot, dot. And then when you have that, it's just n squared times n squared plus 1 over 2. And that just simplifies to n squared. So.
So it's like you take the last term.
It's like it was like a famous story where it was like how you add all the numbers from 1 to 100. It's just 101 times like.
Is that guy right? This guy?
Yeah, exactly. Like and then since we're working in such large numbers where n is like huge, the constants don't really matter. So that just simplifies to n squared times n squared.
Yeah, exactly. Any questions? This case here, or this case?
How would you do this for the first case?
For the first case, exactly. So for the first case, we know we're starting from 1 plus 2 all the way up to n, right? What we were saying is if you know the last term of your arithmetic sum and you know the first term of your arithmetic sum, you take the last term, parentheses, the last term plus the first term divided by 2, right? Let's simplify this. N squared plus n all over 2, right? We know that if we take the theta of n squared plus n over 2, that is here, my bad. Let me put this a little lower, getting cramped up here. This is essentially the same thing as theta of n squared over 2 plus n over 2, right? We know that when we're doing asymptotic analysis, we don't really care too much about the lower order terms. We know that there's something bigger. Like say, for example, we know that n squared is much bigger than n. Therefore, we would neglect that. Simply take n squared over 2. We know that now we essentially don't need to care too much about constants. So that's why theta of n squared over 2 ends up becoming theta of n squared, which is the answer to the original problem. Any questions on this? I think we should probably go to like a recursive. Would you guys want to do another iterative asymptotic analysis question, or would you want to do a recursive? Recursive. How about we do an iterative and recursive one? It's more of the challenging one, but it might be enough for the last question. How does that sound? Okay. All right. Jesus, take the wheel. Okay, let me go back to this. Okay. Okay. So this was the first recursive one I wanted us to go through. The next one that deals with recursion and iterative for loop process is sort of an extension to this, which I think you guys would appreciate. So here we have ghost updated. I'll give you guys like a minute or two to look at this and come up with any ideas, any questions you have. What would be your first plan of attack? If you haven't seen a problem like this before, don't worry. I feel like after this, you'd be able to nail it. So again, take a few minutes on this and we'll resume. Sure. Okay. Okay. Apologies. Is it good now? I started like 53 minutes ago. Okay. Yeah, this is probably like a good meeting. Let's see. All right, so before I go onto the iPad for a solution, let's just like walk through this really quick. So just by seeing the last lines, we know that there's like some recursion happening here, right? There's recursion happening. We know we have the base case somewhere in this method. It's the first line. When n is less than or equal to 1, that is when we've hit the base case condition. So we know when to stop, right? We can't just feed in n equals to 1 into this method and say, all right, kumbaya, let's go home. We have to actually think about big input size, right? So maybe like n could be n equals to maybe 1,000, or maybe n equals 1,000,000,000. Okay, then what now? So n equals some big number, right? I know I don't satisfy that base case condition, so let me go to the for loop. I start at I equals to 0, and I'm traversing this for loop for as long as I is not greater than n. So just from that alone, that tells me that this for loop runs in a linear time, right? It needs to traverse 0, 1, 2, 3, 4, 5, all the way to the nth number, right? Okay. So we know that this for loop is going to take theta n time. Now I'm exiting the for loop. I can finally call my recursive call, right? What am I doing here? I'm essentially just cutting the problem in half. So if I had 100 for my first n, my first function call, n equals 100. Now, n if I do n divided by 2, now the function or the integer is passing is 50. So that means that all of these are also going to be 50 as well. I'm cutting that problem in half each time. But as soon as I call this, right, that means that my recursive stack is going to get deeper and deeper and deeper because, right, we want to finish this until we have hit the base case. So how do we attack these sort of problems? Well, you might have seen something as a sort of tree diagram for these recursive problems. We're going to do that line of approach. So before I do that, does anyone have any ideas of how we could start this? Yeah, what goes on the top of the tree? Exactly. So we can think of each node in our tree, which I'll draw really quick, as a sort of what we're passing into the tree or what we're passing into the method itself. We're passing in a number n, right? So that's exactly how I'll start this. Let's see, I'll do a stop share. Okay. See this fine? Okay. Okay. Okay, so say I pass in a number n to my method, right? Before I do any recursive calls, I need to evaluate how much work am I doing right now. That for loop that I had earlier takes linear time, right? I'll do a little note here just because we don't have to see it. So whatever number I'm passing into my method, I'm doing that amount of work. So I could say that this node here is going to take n work. Okay. And now we saw 4 recursive calls afterwards, right? So the strategy for these sort of solution-based diagrams is you want to do a branch for every single recursive call that we have. We had 4, so let's do 4 branches. Each branch holds a, each direct branch to n will hold another function call. So what did we do? We passed in n over 2, didn't we? So let me just pass in n divided by 2. So say n was originally 100 up here. That means when I call the recursion again, it's getting cut in half. So that means that the n in here is going to be 50. And we can think about that for each of these nodes here. Okay. Now we have to ask the same question again. Each of these nodes is going to do that exact same for loop that I saw earlier. How much work does that for loop do? That for loop did a linear amount of work, right? With respect to the input. So if the input now is n over 2, that means the amount of work that I'm doing is now n over 2 work for this specific node right here that I'm looking at on the left-hand side. Does that make sense so far? All right. So say I do n over 2 work because of this for loop here, right? How about the next node, right? Before we even go further in the call stack, this is a nice strategy that I think you guys would like. Let's evaluate the work at each of these nodes before we keep making our tree like either spindly or bushy, right? So let's evaluate the work done on this one. Just as the left node was n over 2 work, we're passing in the same amount in this time. So n over 2, we will do n over 2 work. The third node will hold n over 2 work, and the fourth node as well, right? Now, when I get to this part, I want to add up all of the work that is done at this stage in the program, at this right here, that I can highlight it. I want to add up the amount of work here, just as I did previously. For the first blue rectangular box, I added n work. Second rectangular box, let me add n over 2 work plus n over 2 work. The third case, the fourth case, right? That ends up being 2n. Once you add all those 4 fractions together. Okay, now we can finally dive deeper into our recursive calls. So I know that each time I call this method, I'm immediately doing 4 different nodes that branch out of it, right? So let me look at this left-hand node again. I'm going to do 4 more branches here. Now, what are we doing when we're opening a new function call? We're cutting the problem in half, right? So in this case here, if my node is n over 2, and I'm doing 4 new branches, and I'm cutting the problem in half each time, that means I'm cutting n over 2 in half as well. I'm cutting n over 2 in half. This comes out to n over 4. So that means that these 4 nodes here, I'm doing n over 4 work, n over 4 work, n over 4 work, n over 4 work. And this same line of thinking applies to all these 3 branches, right? All these 3 nodes as well. And as we see, this is why all of these nodes sort of follow this like multiplicative pattern. You can see here, 1, 2, 3, 4. I won't draw them just because I have space. But if you look at this level now, here, I'll do it in another rectangle. Got to wrap up soon. We can say here we have n over 4 plus n over 4 plus n over 4. You see the redundancy that's happening, right? You guys might like this. There's a lot of redundancy happening. I know I have to do this for every single nest that I have in here. I have n over 4 plus, or 4 times, right, for this nest. I got to do the same thing for this nest, the same thing for this nest, and the same thing for this nest for the purpose of finding out how much work am I doing at this level, right? So let's see. We know that this first nest is, let's see, n over 2. So this first nest is doing n work. N work for this total nest. That means this nest will also do n work, n work, n work. So we have 4 nests, each do n work. So that means we have 4 n work total at this third rectangular box. We do this same thing again and again and again, but now it's becoming redundant, right? Now we can identify a pattern that's occurring. There is a pattern. There's a relationship between the amount of work that's happening at the root node with the amount of work that's happening at the second level and the third level. So I know there's a pattern happening. I don't want to do all of this. It'll take too much time. But I know at the end, I'll hit some sort of base case where I have all these little nodes that have all hit the base case of, what is it again? It is n is less than or equal to 1, n equals to 1 exactly. Yeah. So I'm guaranteed that the size of these nodes are all n equals to 1. So now the problem becomes, how many nodes do I have at this last level? And how much time does it take to go from this top level to the last level of my recursion tree? These are the main ideas you need to be asking yourselves when you're solving these questions. And I guarantee you, you will be able to be successful when you're doing these. So if we look at the first level here, n equals, we have n work. All right. The second level, we have 2n work. The third level, we have 4n work. We see that there's some factor of 2, right, in each time. So how much work am I doing at the last level? Before I do that, let's see if we can come up with like a sort of pattern. If I see the blue rectangle, we see that our method is essentially dependent on height. The work is dependent on height. So I have, say, what if I have 2 to the 0 times n for this first level? What if I have 2 to the 1 for the second level here? 2 to the 2th power, second power, times n, right? We see that the exponent here, let me highlight it. The highlight portion is kind of tells us what level we're at, right? This is the paradigm that you'll follow when you're doing these recursive algorithm analysis. So therefore, all the problem is asking me to do is, if the pattern follows, I have 2 to the last level of the tree, which is the height of the tree, times n. And I'll leave this as an exercise for you to finish. I can stay out later. You guys want me to work it out with you, but I think the show must go on. Yeah, thanks, guys. I hope this helped. We're at the end, if you'd like, I can stay around and see how you can take the sum of the work of every single level in the tree. Once you do that, you will find the answer. Again, there's a few more steps after this, but again, running out of time. No, we have to take the sum of each level, the sum of the work at each level, combine them. And also we need to find out how tall is the tree to begin with. Because we know that the work at each level is a function of the height, right? Again, just to reiterate, the first level I had, 2 to the 0 is 1, right? Times n gives me n. How about the second level? The second level has 2n work, right? But how can I generalize this in terms of height? I can have 2 raised to the first power times n, which gives me 2n. And I keep doing that process for each level. The tricky part is finding out, how do I evaluate this? Because I can't just write 2h times n. I have to do 2, h is going to be some specific value that we have to find in terms of n times that n that was right here. And then we take the sum. And then that would be the answer. But we need to find that out. Okay. Any last questions on this?
And you ask this in the beginning?
Yes, you could expect something like this and possibly even harder. I mean, I guess. I'm so sorry. They come out pretty hard, I feel. I mean, as I'm taught, I mean, they're brutal. Like, I'm not going to sugarcoat it. I can give you my opinions on it at the end of the class, but I don't know. It feels like it becomes less of an asymptotic analysis question, more just like so much like math that you need to know. So Again, I'm welcome to stay later after the review session. We can go over some logarithmic tricks and how to find total height of a recursion tree and how to calculate all the work. But any last times n? Yes, because each level sort of has, we know that before we came up with these solutions here, like 2 to the 0 to the n, 2 to the 1 times n, 2 to the 2 times n, we did like a manual work calculation, didn't we? We did a manual work calculation that the first node will take n work because of that for loop, right? The second level, how much work will it do? I know that each node will do n over 2 work. If there's 4 nodes, that ends up becoming 2 to the n work, right? So that's where that n factor comes into play.
Was the first one?
My bad, it's n. Yeah.
Would be 2 to the n, like,
No.
no?
No. It's a really lovely problem, I think. Knowing how to find the height of any recursion tree is extremely important. They're not all the same. Yeah, the height of all recursion trees, even if you're cutting a problem by some factor, well, I can give it away. The height of this recursion tree is log base 2 of n, right? So it's log base 2 of n. I guess after to give like a more mathematical reasoning behind that, but the height is log base 2 of n because it takes log n time to cut a number by 2, 2 by 2 by 2 by 2 until you reach that base case of 1, no matter how big that number is. Log base 2 of n. So the height is log base 2 of n. I attach that height now to the exponent because that's the generalization that we made, right? 2 raised to the height times n, 2 to the log n, 2 to the log base 2n ends up just becoming n.
It's a mathematical. Do like at b raised to log base b on any integer, like if you could slash out to or b
Yeah,
whatever that.
this is like an identity that we exactly would use. And feel free to come by afterwards. And then we're still not done. There's still a little more to do, but yeah. You guys good? Yeah. Sorry. Okay. Now switch between them. Do I just like, let's see.
You're muted. Oh, so sorry. Yeah, hold on. Let me like go through that really quickly again. But yeah, so yeah, disjoint sets, we have two important operations. Connect with connects two things, is connected, which returns true if they're connected, and not true if sorry, false if they're not connected. And then yeah, and then we just went through a quick little example. But yeah, I'll just speed through it so we can get to the other stuff. But yeah, so there are four implementations pretty much that we go through in 61B, which I'll go over one by one. So starting with quick find. In quick find, we use an array to represent the disjoint sets. And for each sort of ID, so for each element, which corresponds to an index, it stores sort of like a set ID that represents which set it's a part of. So in this array, we can see that 0, 1, 2, and 4 are all part of the same set, and 3 and 5 are part of the same set, and then 6 is on its own in its own set. And so it's called quick find because find or like is connected is very quick. Like we can just check the ID of two elements to figure out whether they're connecting. But when we're doing the connect operation, we have to like scan through the whole array, which is very slow. And so for a quick example on quick find, yeah, so I'll just like go over the array really quickly. So like 0, 1, 2, and 4 all have set ID 4, which represents the fact that they are all in the same set. 3 and 5 have the set ID 5, which means they're in the same set, and then 6 is on its own. And so if we connect 2 and 3, we want everything in 2 set and everything in 3 set to have the same ID. And so we could have chosen 4 or 5 in this case, but in this case, we just choose 5 to overwrite all of the elements in 2 set. So now like 0, 1, 2, 3, 4, and 5 all have the same ID. Any questions for quick find? Yes. Oh, is it always a smaller one? Oh, sorry. So for quick find, it's kind of arbitrary. We just choose one of the numbers. We will be connecting like smaller to larger, maybe in like quick union. Good question. But yeah. That's for quick union and weighted quick union. So this is the one of the first implementations that we're considering for disjoint sets. So this is just like a different way of doing things. Oh wait, sorry. Oh yeah, so sorry. Like that. Yeah, good question. So connect is or the constructor. Yeah, so the constructor is logN. Sorry, the constructor is n because we have n elements in the array. So we're just going and creating an array of size n takes n time. So like if you make an array with one element versus like an array with n elements, like the array of n elements is like scales with like the number of n. Yeah. All right, I'll move on to quick union. So quick union also uses an array representation of disjoint sets, but we have sort of a different representation. Instead of storing sort of like a set ID and all of the elements storing like the same ID, we have like a different way. So an element stores -1 if it's a root of a tree. You can also say that it's when it has no parent. Otherwise, if it has a parent, then we store the index of its parent or the element that is its parent. So in this array, we can see that 0 has -1, which means 0 must be a root. And for 1, 1 is storing 0, which means 1 must be the child of 0. So 0 is the parent of 1. And yeah, so union is a bit quicker because all we have to do is like, if we're like unioning 2 elements, all we have to do is like change 1 index value. And this might make a bit more sense when we go through the example. But yeah, so quick little example. I'll just run through the array really quickly. So like 0 is -1, which means it's a root. 1 is a child of 0. 2 is also a child of 0. 3 is a root. 4 is also a child of 0. 5 is a child of 3. 6 is a root. And 7 is a child of 1. And so we'll have this tree representation here. And when we call union, so union is the same as connect. So what we do is we find the root of 5. So 5 sees that its parent is 3, so it goes to 3. And so we know that the root of 5 is 3. And then when we find the root of 2, so 2 goes to 0, and then we find that 2's root is 0. And so then what we're going to do is, instead of having a -1 at 3, we're going to take 3 and change its parent to 0. And then now this effectively connects all these elements together. Yes.
Second one.
Yes, exactly. And so we'll see why this can be bad in like a quick second.
Did you attach it to bigger tree or the more?
So we're going to take into account size when we go into weighted quick union. So this is a bit more of like a naive implementation so far. Good question. Yeah. So this is the result. I'll go through a bit more quickly, but with just quick union and not weighted quick union, we have this like worst case of connect operations, which leads to like a very spindly tree. And so it's going to be very slow. That's just like the gist. And the solution is using what's called weighted quick union. And so instead of just connecting one of the trees to the other, now we're taking into account the size of each of the trees. And so the size has been found to be like a good proxy for height, which is what really matters. And so what we do is we connect the smaller tree to the bigger tree. And so this results in tree heights of logN, which improves our connect and is connected runtime to logN instead of n like it was in quick union. Any questions?
What is the tree?
Yeah, good question. I'll go over that in a second. So just like a quick example, in a weighted quick union, if we're connecting like 0 and 3, 3 is the one with less elements. So we'll make 3 a child of 0. So this one would not be possible for a weighted quick union because we're connecting the smaller one to the bigger one. So this one has a lower height than this one, which is why we do this one. But yeah, so quick little performance demo. So like this is like the absolute worst case for a weighted quick union. So if we like always connect an equal amount of elements, then we'll sort of end up with like this situation where like for every increase in like the height, we like sort of are able to double the number of things in our set. And so I'm just going to go through it really quickly, go through all this really quickly for the sake of time, but this is what like the weighted quick union worst case looks like, and it is logN. Oh, I think you need to plug it in to battery. Yeah. Yeah, and there's one last optimization that we make in weighted quick union, which is called path compression. So here we just like connect the smaller one to the larger one, but with path compression, we're sort of like doing an extra optimization on top of that. And so I'll just go through the example. So like path compression is basically just whenever we like see a node, we connect it to the root of the tree. So when we do is connected on 7 and 4, yeah, we like find like the root of 7. So 7, we see 7 and we see 6, and then we go to 0 and we see that 7's root is 0. And so we're going to take all the nodes on this path and make them a root of 0. So instead of 7 being the child of 6, we'll just make 7 directly a child of 0. And the same goes for 4. So when we sort of climb up the tree for 4, we see 4 and then 3 and then 2 and then 1. So we make everything along the path. So 1, 2, 3, 4, a direct child of 0. Yeah, any questions about path compression? Yes. Yeah, that's a good question. So 5 is a child of 2. And so for path compression, we only make the nodes that we see. So when we're climbing up the tree, we only see 4, 3, 2, and 1. And we don't see 5. And so 5 just stays a child of 2. Yeah.
You guys also may have seen, I think did you guys do the disjoint sets lab yet?
Yeah.
Yeah, I think you guys recursively designed this such that when you traverse up, every node that, like exactly Andy was saying, ends up being attached to like a pressure.
All right. So that's a summary of all the runtimes. I think this would just be good to like put on the cheat sheet. And then I don't think we have time to like work through this problem, but I'll just like run through it really quickly. Okay, how do I do this?
If you want to,
Okay.
yeah, then you can see the table. My bad. Where did your slides go?
Okay. Yeah. So I'll just work through this really quickly. So we have an array.
Notebook. You gotta stop sharing. Sorry.
Oh, I need to see the.
Let me see.
Oh, can I control?
Yeah.
Oh, wait. Whatever. It's fine. But yeah, so like if the array is like this. So another thing about weighted quick union is we store the weight as a negative number of the root. So I'll just run through this array really quickly. So 0 is negative, which means it must be a root. 1 is a negative, which means it must be a root. 2 is a child of 0. 3 is also a root. 4 is child of 0. 5 is a root. 6 is a child of 1. 7 is a child of 1. 8 is a child of 3. And 9 is a child of 2. And so the first question asks how many disjoint sets there are. And so if you're just looking at the array, you can just count the number of negatives, and that'll give you the number of disjoint sets. And then part B asks what happens when we call connect on 4 and 9. So after drawing it out, we can see that 4 and 9 are part of the same disjoint set. And so in this case, nothing will happen because we just find that 4's root is 0 and 9's root is 0, which means they're in the same set. And so the number of disjoint sets there will be is also 4. And then finally for part C, if we do connect 4 and 9, if we do connect 4 and 1, then so 1 is this disjoint set, 4 is this one. And so we'll connect the one with less elements. So this one's size 3, this one's size 4. So we'll make 1's parent 0. And so the height here is not going to change. It's still going to be correspond to like the height is going to be 2 because that's like the longest distance from the root to any of like the leaves. So like 9 to 0 is 2 edges, and then 7 and 6 to 0 is also 2 edges. Sorry, it's a little bit messy. But yeah, any questions? Yes.
Yeah, for part B, if we call it the path compression, what would change?
Yeah, good question. Yeah, so yeah, so the reason it's specified is because it changes if we do path compression. So here we're just connecting one tree to the other, but if we do path compression, we're connecting everything along the path to the root. And so like if we did path compression here, we'd be connecting like 9 to 0, and like also 2 and then like 1 and then like 7, for example. I won't write it out for the sake of time, but like that's basically what happened.
But I mean, like, here anyway, 4 and 9 are in the same, yeah, so no four, makes sense.
Oh yeah, so here there's like now 3 disjoint sets.
No, this case will be,
Oh, yeah, so path,
they specify it without path compression.
yeah, so without path compression or with path compression, it doesn't change the number of disjoint sets. So you're still connecting them, but the number of disjoint sets does not change.
It doesn't matter what it's mentioned.
Yeah, it's just like for a specific, like for clarity, basically. Yeah, good question. All right. Yeah, so this problem is I think spring 23, midterm 2. But yeah, I think let's move on to the next topic. Oh, I need a screen share, right?
I think it's good
For like
the desktop.
this.
All right, so we'll be going over trees. Trees. So first, our first tree structure is the binary search tree. And some of the properties of a binary search tree are that for every single node, the key to the left subtree is going to be less than X's key, and the key to the right subtree is going to be greater than X's key. And there are no duplicates. So these are just, how you can check if your binary search tree is valid. And let's practice doing some insertions so we know how it behaves. All right, so we have this binary search tree from our previous slide, and we want to insert 9. So what we do here is we check, okay, so 9 is greater than 4, so we move on to the right subtree. 9 is greater than 6, we move on to the right subtree, which is just 7. And then because there's no more values under 7, we'll insert 9 there. And this is a valid tree. Now, if we want to insert 8, we do the same thing. We go from 4 to 6 to 7, but now 8 is less than 9. So what we do here is we insert 8 to the left of 9. All right, now let's go over removals. If we want to remove the node 6 from this tree, we can do something called Hibbert's deletion, which is where we find either the greatest value in the left subtree or the smallest value in the right subtree, and then we replace the value we want to delete with that value, and then we connect all the children nodes of that deleted node to its parent. So an example of this here is we delete 6, right? We want to delete 6. So we can either exchange 6 with 5, which is the greatest value in the left subtree, or 7, which is the smallest value in the right subtree. And here, because this subtree is, or we should be looking at this tree. Since this subtree is greater, I'm going to choose 7. So then we replace 6 with 7, and then we connect 7 subtree, which is this portion, to 6, or this node, which we now replace with 7. So it's going to look like that. Now we want to remove 4. So this is the same thing. We use Hibbert's deletion. We either we go and find, okay, so 3 is the greatest value in the right subtree, in the left subtree, and 5 is the smallest value in the right subtree. We can choose either one of these to replace 4 with. And because I'm seeing this subtree is greater, I'm just going to choose 5. So we replace 4 with 5, and then we delete 5. And there are no children for 5, so this is just good.
You have a question?
No.
So it's either the smallest value in the right subtree or the greatest value in the left subtree?
Yeah.
And it's based on like which subtree is bigger?
No, you can choose either and it'll be valid, but like usually I like to choose that, or I chose that here just for convention, but you can choose either. Yeah.
And also specify.
That too. Okay. So as we saw in this previous example, right? If we constantly add numbers to this tree that are greater and greater, we can create a tree that looks like this, which is spindly. And if you want to find a value in this tree, you're going to go, say you're trying to find Z, right? And Z is greater than K, so you go to you go to the right subtree, and Z is greater than V, so you go to the right subtree, and Z is greater than Y, so you go to the right subtree and find Z. This is, you're traversing the entire length of the array, and you're traversing every element in this tree. So that would take theta n time. But if you have, say, this many values and you want to find Z, you would do the same thing, except you would now avoid traversing all of these other values. And this is what we call a bushy tree, and this is what we call a spindly tree. And as Matthew said in his asymptotics presentation, I think usually for bushy trees, it's better for your trees to be bushy because this is the best case runtime, whereas this is the worst case runtime. So you want to avoid spindly trees and you want to create bushy trees. But that's not guaranteed with the binary search tree data structure. So how do we guarantee this? How do we maximize the bushiness of our trees? We use something called a B tree. So what we do for a B tree is instead of having just one value for each node and then moving and then attaching when you want to add nodes, you attach it to to either the right or the left. We have a limit for the amount of values we can have for each node. And the trick is when the number of values in that node is greater than the limit, we take the middle value of that node and we move it up. And this way, we're always going to have a bushy tree because we're always going to have a node with a left subtree and a right subtree instead of just like a very spindly long tree. So these are some properties of a B tree. And this is an example of a 2-3 tree because the limit is 2 and 2-3 represents the number of possible children each node can have. Right. So let's practice some insertion for a 2-3 tree here, since we see the limit is 2. We want to insert 9 to this tree. So what we can do is, it acts just like a binary search tree, except we have more than one value in each node. So let's start from 17. 9 is less than 17. We go to 13. 9 is less than 13. We go to 5. 9 is greater than 5. But notice that this node hasn't hit the limit yet. It only has one value. So what we can do is simply add 9 to the right of 5. And this would be a valid 2-3 tree. But now what happens when we hit the limit? So let's try inserting 26. Just use the iPad for this.
Here you go.
Still need to see the tree though.
You could, it's a little tricky. Cool.
Okay.
Oh, there we go.
Oh, nice. Okay.
Let's take this out. Okay, so you just draw the tree.
Oh, that's the answer. All right, I'll just draw this tree.
Okay. And then Jeff, feel free to go back to this app.
And we're trying to add 26 to this tree. So if you're working from home or here, you can, try to solve this yourself while I write this out.
I feel like on an exam, it's typical of that to throw some insertions at you as like mechanical problems for 2-3 trees. The hardest part of this would be, inserting something that breaks the invariant, therefore you could propagate the node upward or if you choose the right spot, seeing what to split. Feel free to email me. I can send you like a good slide that I found that has like farther edge cases of what to do in that case.
Okay, so we start from this node, right? We have, oh, stop. Sure. It's just lacking. Right, so we start by recognizing that this is breaking the limit. So we want to take the middle node. We want to take the middle node and move it up. So this would look and we want to split up the bottom, the other two nodes to maintain its bushiness. We also recognize that here, this is also overloading. So we'll also move the number 23 up because that is the middle value. And then we will split the remaining ones. Okay, and how do I go back to share? And we see that that's the answer. Okay. Slide.
So every time you switch, you have overloads and then you.
If right, if the number becomes greater than the limit, then you split it up into two subtrees and you move the middle node up to its parent. And this is like a chain reaction. If your parent node also has too many, then you do the exact same thing all the way until the top. And if your node is the parent, let's say we added some more numbers and then this node also got overloaded, then we would take the middle node here and then we would move that up to make it a new parent. And then the right subtree and the left subtree would, it would become left subtree and the right subtree and it would maintain its bushiness. So that's how we ensure that our tree stays bushy and it's optimized for searching.
The limit always 2.
For a 2-3 tree, the limit is 2 because the possible children for your tree is either 2 or 3. If you have, let's say the limit is equal to 3, then it would be possible for your tree to have 4 children. So that would be called a 2, 3, 4 tree, so on. This is not. Oh, maybe it's because I'm on the screen share and not on the actual slides. Or oh no, never mind, it works. So how do we implement B trees, right? The actual implementation of B trees is kind of annoying to do. So what we've done is we can create something called a left-leaning red-black tree. And this way we're taking advantage of our binary search tree structure and then slightly modifying it so it can act like a B tree. So how do we do that? We have 2 different colored nodes, and we can use the red node to represent a node with 2 values. So for in a 2-3 B tree, right, we can connect 2 nodes, let's say 13 and 17, with the red link, and that would represent 13 and 17 in the same node in the B tree. And this is very handy. So we can use pretty much all the other properties of a binary search tree. And notice that we say left leaning because we want all the red links to lean to the left or to go to the left. So this would mean that all right leaning red links would be invalid. And all the other properties of the B tree also hold. This would mean that we can't have more than 2 items linked with red links. So this would also mean that we can't have, let's say 17 linked to 13 with the red link and then 13 linked to 9 with the red link. That would represent 9, 13, 17 in the B tree, and that would be overloaded. So we would need to do something. So what are the operations that we should implement to ensure that all these properties are met? We have 3 operations: color flip, left rotation, and right rotation. So for color flip, we're basically flipping all the colors of the links connected to the node we're color flipping. So for example, here, 2 and 4 are both connected to 3 with a red link, and this would represent 2, 3, 4, which is overloaded. And what we want to do with that is we want to move 3 up, right? So it becomes the parent, and then 2 and 4 become its children. So how do we do that? We simply color flip, and then 3 becomes the parent, and then 2 and 4 become subtrees, right? And here in this case, we have a right-leaning node, right node that's red, and that's invalid. So what do? We rotate. We do left rotation. Basically, we're rotating all these values to the left. Like, imagine this is like a pulley, and the node we're rotating is like the wheel on top. And what we're doing is we're pulling all these numbers over to the left. So what happens is 4 now becomes the parent with left leaning red link to 3, and then with a subtree of 2. And notice that this is actually equivalent to this, except now it's valid for our left leaning red black tree. And here we have 2 nodes that are red connected together. This would represent 2, 3, 4 all in one node, which is incorrect. So what we do here is we want to have a right rotation. So we're pulling the pulley this way now, and then for 4 now becomes, this should be 4 actually, not 3. I'll change that later. So 4 now becomes this, and notice that this is still an invalid tree. So now you need to do the color flip operation in order to make it a valid tree. So here we have 2 examples of invalid left-leaning red-black trees. Does anyone have any ideas of what we should do? Yes, a right rotation, right? Now is this valid? Yep. And now we have a valid tree. What about this example? Yep. All right. Now we have just any questions before we move on? Okay. We have a practice midterm question from spring 2019. And we're trying to add 15 to this tree. But when we add 15 to a tree, it's not valid. So how do we make it valid? Also, side note, whenever you want to add a node to a red-black tree, you always add the node as red, as a red link. It's just the same as the B tree. When you're adding like a node, right? You're not gonna add like another subtree. You're just gonna add it to like the node that it's in, and then if it's overloaded, then you correct it. It's the same thing for this. You always add it as a red link, and you correct it afterwards. So this is the valid place for 15. Rotate left. And what would you call it on?
15.
All right. Now we have the second part of this question. And we have we're adding 40 now. I can do this on iPad. I think they removed this one. Yeah, like that. Oh, no, 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 no. Uh-oh, go back. How do we go back?
Wait, to what?
The slide. Oh. Sorry.
Also, a note, as everyone's working, we're running a bit behind on time, but there's no one in this room after us. So if you guys are okay staying here, I think we're gonna continue going at the pace that we're going at in order to complete all. But if you do have to leave, this is being recorded and it will be up to the later tonight. Yeah, it's food challenge.
I don't know why it's okay. So let's go over this problem. We want the operations for how to make this a valid tree. So we start from the bottom and notice that we have a right-leaning red link here, and we don't want that because it's a left-leaning red black tree. So does anyone have any ideas as to how we can solve that?
Rotate that from 3 9.
Yep. Oh my God, this is kind of interesting. There you go. And what that would look like is like this. But now we have another problem. We have 2 links here. So what can we do with that?
Rotate right into the
Rotate right on 43. Yep. So that would look like, I'm just going to draw it. Okay, now what? Oh. Does anyone have any ideas? Notice we have two red links here. Right, color flip on what? Yep, that's correct. So okay. And are we done?
No, one time, color flip.
Right. And
25.
on 25. Okay. I think we just go back to the laptop now.
This is like the easiest level of difficulty for this exercise, or that's what we should expect.
I think, as long as you understand like all the rules and like how the thing works, I think like you should be fine.
It's pretty straightforward.
Yeah.
You just need to have those rules down.
It's not gonna get like super hard, but then what is it?
There's not that much more they can do to make it more complicated. I mean, it's
Yeah, they're just testing you on your understanding of this data structure. So
Just find a way. And it's wouldn't be surprised.
Let us know if they do.
I agree with what Justin and George said, but also like, I think like the tricky part about this topic is the fact that you're going from a binary search tree to a two-three tree and then to an LLM. That's really supposed to be because they're all three of them are related, it's kind of like a progression. The tricky part of this topic is really supposed to be, okay, like taking this binary search property and thinking about and then in an LLRB. And be able to.
So they can ask us to like switch it back when.
Exactly.
Yes.
Yeah, I would, if you guys are like rusty on that, perhaps like they could maybe look at two problems where it's like, all right, given this LLRB, what is the one-to-one corresponding two-three tree that relates to this? That's
Yep.
totally fair.
just like this question, which is draw the 2-3 tree from this part. It just without this 40 here. So here, notice that 25 and 17 are connected with the red link, right? So that would mean they're in one node, and 25 is at the top. So we would also put 17 and 25 in the same node, so that those would be at the top. And it has three children, 13, 22, and then 43. And 43 is connected to 39 with a red link. So that's what the tree would look like. Any questions? Okay, nice. If you have any questions on Zoom, feel free to put them in the chat. I'll try to get to them. Yeah. Okay.
All right, I'm going to be covering graph and tree traversals, but I kind of wanted to start by asking, what have you guys learned about this? Because I was checking the schedule and you guys maybe had one lecture introducing traversals, is that right? Can we get a show of hands of people that went to Friday lecture and learned about it or heard about it? Okay, completely understandable. Yeah, okay, totally understandable. I'm hearing an echo back here.
Oh, it might be the mic. There's like a mic down there.
Oh, down here? Nothing we
Yeah.
can do about that?
No.
Okay, that's fine. That's fine. Okay. Well, let me just go through conceptually then. I don't think the midterm will go too deep into graph traversals. Over the next couple of weeks, you are going to learn quite a bit about this, but I'm expecting for this midterm, you only need to really know kind of the conceptual traversals and how they work, but not necessarily all the applications. But I'll do my best to cover all of them, and then you can always reference the slides. I kind of want to start by just differentiating trees versus graphs. you're going to hear those terms thrown around a lot, but they are distinct. Graphs are kind of the larger, more universal topic that you guys are looking through. It basically consists of nodes and edges and how those connect to each other and form different kinds of states. Trees are a subset of graphs that are connected and acyclic, meaning that yeah, I mean, it literally resembles a tree. So BSTs, for example, are a tree. 2, 3 trees are a tree. They're also graphs, but trees are a subset of graphs. So right here, this kind of just lays out the terminology that you'll see under each of those terms. You don't need to know, I guess, super specifically, but in case you're wondering, you might hear like a term pre-order thrown around. That can refer to both, but sometimes when we say DFS or BFS specifically, we're talking about the graph traversals. So just something to keep in mind. Probably the most important concepts that you want to take away from this little mini lecture is the difference between DFS and BFS. So DFS stands for depth first search, while BFS stands for breadth first search. This is a really, really fundamental data structures topic that you'll probably see in many other classes if you're like data science or CS specifically. But DFS has to do with going deep, hence why it's called depth first search. So if you think of a tree, if you think of like a 2-3 tree, if I'm traversing it, if I'm visiting the nodes, if I'm running DFS, then I'm basically searching really, really deep first before I come back up and kind of search the next one and then go deep again. So we'll see a couple visual examples later, but the 3 different traversals that we'll learn about here are pre-order, in-order, and post-order DFS. For BFS, this is completely the opposite. Instead of searching deep, we're searching wide. That's why it's called breadth first search. If you guys have seen or heard of level order traversals, it's very analogous or similar to that. And the specific definition for BFS is that you always want to visit a node based off of the order of the distance from some sort of source node or root node. So I want to visit all the nodes at distance 1 from the root, and then all the nodes at distance 2 from the root, and then 3. So if you think about it, it's a little bit of a flip from DFS. But yeah, let's see some examples. Depth first search, like I said, it has those 3 different traversals, pre-order, in-order, and post-order. So let's look at each of those. First, I kind of want to give an intuitive trick that you may or may not have learned in last lecture, but it's something that I picked up when I took the class that I thought was really, really helpful. You don't even have to really have an understanding of how DFS works, but if you just memorize this trick, you're pretty much set to being able to find out the order of nodes that you visit if you run pre-order or post-order, for example. So you see these pink lines here. The way it was explained to me is if you imagine kind of taking your pencil at the top of this tree and kind of drawing around every single node from the left side down and then in between every node and then coming back around to make a cycle at the end, you kind of get this pink curvature. And that's basically what you want to keep in mind as you do these traversals. And whether you're pre-order or in-order, post-order, it's going to dictate the direction in which, or basically at which point you're going to add the node that you visit to your list of visited nodes. So for example, pre-order, the key word here is left side. So as we go through this tree, following that first long pink arc, as we hit the left side of every one of these nodes, we add that to our visited list of nodes. So yeah, let's just walk through that quickly. I have a little animation here. So as we come down, we visit the left side of D, so that's immediately visited, and then B, and then A. Once we get to the end of this, once we've searched as deep as possible, then we start to come back up, but not fully, because the subtree that was right above it also had a recursive call, so we need to come back down. So this is kind of how the recursion works, and it ends up so that we can do this little visual trick where we just kind of follow the curvature of the nodes, and every time we pass the left side, we add it to our list of visited nodes. Any questions on this trick? Sweet. So in order, I'll just kind of blaze through this quickly. It's the same thing, but the key direction is underneath the node. So now you're going to add every node to your list of visited nodes if you pass the underside of the node. So we actually start with A, because if we were starting at D, we actually only pass by the left side of nodes until we reach the deepest part. So the first node that we actually will visit and add to our list of visited nodes is D, or sorry, it's A, and then it's B, and then C, D, E, F, and G. Does that make sense? Great. And then post order is the last one. You will add it to your list of nodes every time you pass by the right side of a node. So in this case, the first vertex that we add is also A, but for a different reason, because we pass by the right-hand side and not necessarily the underside. So then the next one would actually be, actually, I think this is out of order. I think it would be C and then B. Yeah, actually, I wrote down the correct sequence there, but the arrow's out of order, so I'll fix that later. But it would be A and then C and then B, and then not D because we only pass by the underside of D. We can't actually get to that right-hand side visually because we still have that whole right subtree to go through first. So the next one would be E, and then G, and then F, and then D. So that's our final sequence. Everything good? This is a really, really helpful trick. Like I can't emphasize enough. Yeah, you don't have to fully understand how DFS works, but if you kind of know this trick, it will help in like 80% of like the traversal problems. Yeah. So if you want to know how exactly DFS works, though, here's a quick little slide that you can reference later on like the implementation. This is kind of a naive pseudocode for specifically tree DFS, specifically for BSTs actually. And the key differences between pre-order, in-order, and post-order is the position of this print statement here, where we actually will print the node. But it doesn't have to be print. It could be anything. It could be like adding that node to the list of visited nodes. But I think the key idea here is that you do the action at the specified position in the pseudocode. So for pre-order, you always want to do the action first and then do your recursive calls. For in-order, it's always in between those recursive calls. And then for post-order, it's always at the end. Hence why it's called pre-order and post-order. And then you'll end up getting the desired behavior like we've kind of seen in these visual examples. So you can think about that a little bit, but this is the implementation. Any questions so far?
I think we're gonna be required to use the implementation.
In my experience, oh, actually, yeah, maybe. And we'll see a quick example at the end. Yeah, I would definitely like copy this on your cheat sheet if you can't remember. It doesn't take that long and it may come in handy. We'll see an example later. So yeah, maybe. Okay, BFS is pretty quick. I don't even have an animation for this because I think it's very intuitive just visually. I mean, in a tree situation, it literally just means that you visit the root and then you visit everything on the first level, so B and F, and then everything on the second level or third level, A, C, E, and G. It technically doesn't matter whether we visit B or F first, or A or C or E or G in that order. It kind of depends on the specific specified behavior or tie-breaking scheme that the question may tell you. But in general, you're going to be visiting everything at distance 0 from the root, and then distance 1 away from the root, and then distance 2, and so on. So for the tree case, it's pretty intuitive, but I'd say for graphs, which is kind of the more universal thing that we can run BFS on, it's a little bit harder. So you have to remember the rule is that we're visiting everything in order of distance from the source node. So in this case, if we specify the source node to be the one on the left at 0, then if we were to run BFS on this, right, it's not as visually intuitive because it's not kind of stacked nicely like a tree from the top down, but we would visit 0 first because that's distance 0 from, and then we visit 1. That's the only node that's 1 distance from the root. And then we visit 2 and 4 together. It kind of doesn't matter the order again. But those are both, right, 2 edges away from 0 or from the source node. So we kind of keep going until we reach or until we've traversed the entire graph here. Any questions here? Here's a quick slide on some applications of DFS and BFS that I actually looked through the slides from yesterday's lecture, and it looks like they do introduce this problem of like shortest paths and kind of how you can how you can use BFS for solving that. I personally don't think you're going to see this on the midterm, but I might be wrong. So if you want to copy this onto your cheat sheet, that's probably something I would do, especially like these efficiencies and these runtimes. That might be helpful. But yeah. Do you have a question?
You could also do DFS for the graphs, no?
Yes, absolutely.
And then just do the same thing.
So for graphs, it's also sometimes a little bit harder. Like you may find that you can't always kind of do the same like curvature. So for DFS, the trick is you want to travel as deep as possible, right? So for a graph, that would look like going all the way to 7 first, because that's the farthest node from S, and then coming back. Yeah, in this case, you can't really do that visual trick because it's not a tree. It's a little bit more involved. I'm not going to say too much on that for the sake of time. But absolutely, you do run DFS on graphs as well. So this is where it kind of takes a little bit more of an understanding of like how DFS works under the hood. So yeah.
Like same distance away doesn't matter, like how like 6, 8, or 8, 6 is the same thing.
Yes, so usually you'll have to take a look at like if they specify some sort of tiebreaker, like visit the nodes in alphabetical order, for example. That would kind of, or in this case, it could be like visit the node that is lower in value. Usually they'll tell you something like that. But in general, yeah, it doesn't really matter. You want to visit all of those kind of at the same time.
Same thing for DFS.
DFS, yeah, they should specify a tiebreaker, but DFS is a little bit different because
For level 1, you can get, yeah, for like in a tree, same thing, just the same time frame.
yeah.
If this is like in scope for the midterm, like this sort of traversal, I found like I really liked looking at like discussion worksheets of like, they'll have a problem like this where they'll be like, okay, implement DFS on this starting at like a node 6, for example. Usually it's like, no, it's something relatively simple like 0. But yeah, I remember that being on the final, I think. And I actually I think it was in my midterm too when I took the class with your professor. So yeah, if you want more problems like this, like definitely look at like discussions, even like previous semester discussions, they'll have the mechanical problems of this.
Good point. So let's quickly look through a couple of questions. For the sake of time, I'm just going to walk through them with you guys quickly, and then you can always reference these slides later. This question was taken from the final when I took the class. I think it's a really good representation of like a typical traversal problem where you're going to need to know like how pre-order and post-order works. So if you want to take a second to kind of read this, essentially, you have this tree which represents a neighborhood. Each one of the nodes is a house, and they're all kind of connected in this manner. And I guess you're trying to sell cookies here, and you're trying to make the maximum, you're trying to sell the maximum number of cookies and make the most money. So the first question is, what is the total number of cookies Fish sold after calling sell cookies on 6 houses? So this is the code for basically Fish. So this is kind of Fish's behavior here. And the trick here is you want to look at this and be able to recognize that this is a DFS problem because it matches that implementation that I showed in the slide earlier, right? If you go back up here, very, very similar. We have a base case where we have like null as the node, and then we have usually 3 statements, 2 recursive calls and 1 action. And the ordering of the action is kind of what decides whether it's pre-order or in order or post-order. So here, very, very similar, right? We have a base case if the house is null, and then after that we have 3 actions. We have 2 recursive calls. 1 is to search left in the tree, 1 is to search right, then we have the action. So what kind of DFS traversal would this be? Yeah, pre-order because the action goes first before the recursive calls. Exactly. So then all we need to do is kind of look at this tree, and now we can literally do our visual trick here. For the first 6 houses, actually, because it says if we call sell cookies on 6 houses. So we're just going to be doing it until we visit 6 nodes. So if we do that, we start at 1, right? Because we start at the top, visit the left side, right? So we count 1, we count 4, we count 0. After we get to the end of that subtree, we kind of go in between there. And the next node that we would hit on the left side is 6, and then 7 and 8. And that's 6 nodes. So then we would add up the values in there because this specific question is asking how much or how many cookies you would make. And the values in these nodes represent how many cookies you can sell at that house. So if you add up those, you will get 26. This is kind of the visual representation like we saw earlier. Make sense? Okay. Second problem. This is a little bit more tricky. Can anyone tell me what kind of traversal this is? Post?
This right first and then left.
Exactly. So yeah, actually you can call it 2 different things. I think in like one of the solutions it's like called reverse pre-order, but the way I think of it is more of a flipped post order. But yeah, because the action goes at the end, I would call it post order, but you're exactly right that they flip the order of how we search in the recursive calls, because usually we search on the left side first and then the right side. But in this case, it's flipped. So in terms of the visual representation, what we would actually do is we would start searching on the right-hand side. It's like we were doing that visual trick, but flipped. So we start from the top still, but we go down the right-hand side. And post order, if you remember, usually you will add the nodes to your list of visited nodes if you hit the right-hand side. But that was from the perspective of traveling from the left side at first. So post order, it's not really that you always check the right-hand side, it's that you check the opposite side of kind of the direction that you're traveling in. So for this case, if we are traveling down the right-hand side, then we will add it once we see the opposite side, so the left-hand side. And if you want to think about why that's the case, it's because post order has to do with only doing the action after we have like gone through the left and the right subtrees and found nothing and basically finished those recursive calls. So like getting to this leaf, for example, 9 is the first time that we've basically been able to successfully go through the child.right and child.left recursive calls. I call it reversed. I call it flipped post order. So post order from the opposite direction. Yeah, but there's no like official terminology for that.
So essentially, same as if you draw like clockwise now and still check the left side instead of going counterclockwise.
Well, normal post order, you would check the right-hand side. So this case, we actually are checking the left side instead. Because we flipped it, we also need to flip
Yeah, but
direction. Let me check.
right, like the big line,
Mhm.
just draw it now, but instead of drawing like counterclockwise, you do clockwise.
Yeah.
And still check the left side.
You draw it clockwise. Well, we are going clockwise here because the first one we would add is 9. But yeah, exactly. Yeah.
So
Why are we starting at 8? So actually we're starting at 1. So this is why it's a little bit confusing because according to like the visual trick, because we are searching right first, in this recursive call where it says chips house.right, that's kind of our hint that we want to start going down the right-hand side instead. So 8 is actually the last one that we visit. Yeah.
If we couldn't get what's the value of how many cookies we sold, we just skip it. We don't count it as part of the houses, right? It's like here the first time we go over
Yes.
5, 9, we just
Yes. So officially, you would say that you haven't visited or explored that node yet. Even though we've technically like passed by it, we didn't visit it. So you're right, you wouldn't consider it added yet. Yeah. Okay. Yeah, for the sake of time, I'll move on, but like you can stare at this later and kind of like reason why it works that way. This last one I'm not going to go through, but this is an example of how you might need to know the implementation of how DFS works, because it asks you to kind of construct a modified version of DFS where you look at the sequence here, it's spitting out certain numbers twice, specifically the zeros and the 8s and the 10. So if you kind of look here, the zeros and the 8 and the 10 are the leaf nodes. So we might think about some sort of modification where we might do an action twice, but only for the leaf nodes. And it turns out, and I'll just give it away, that you do the action at the beginning and at the end. It's kind of a mix of pre-order and post-order. But yeah. Any final questions on graph or tree traversals?
Just the last one, why would it work if you do tree and post?
It's not exactly that we're doing both of them, but for example, we just think about the recursion itself. We start at 1, and this sequence already tells us that we are wanting to do a pre-order traversal because 1, 4, and 0 are the first 3 values. So if we think of that visual representation, it's kind of the same thing as like, if we start on the left-hand side, so we pass by the left side, we're going to add it. But there's this added thing where the 0 is doubled. And that can only happen if once you've gotten to the leaf node, once you've gotten to the end of this house dot right, you have one more action to spit out that value again. But that only happens once you hit a leaf node.
So post order, you only check after you only like return after you check the right and the left and right. And then pre-order, you just return as soon as you see it. And then in order.
In order is like in between. So it's like if you have traveled the left-hand side, but like not the right-hand side of the subtree.
It checks left or checks one side.
It checks one side. Yeah. 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 This is confusing stuff, but that's why the visual trick is really helpful, because it's easy to get kind of lost in the details. And then if you want to start thinking a little bit further about it, then take a look at that like slide with the implementations and then take a look at these examples. Yeah. Sweet.
All right, next topic is hashing. Yeah, so what is a hash table? So a hash table is a data structure that stores items in a way that they can be checked and accessed fast. And so the implementation that we go over for hash tables in this class is an array of buckets where each bucket is a linked list storing the items in that bucket. And so generally each object or primitive type will have a hash code function that can be implemented in Java. And yeah, so there are 3 steps to inserting into a hash table. So the first step is to get the hash code of the object. The second step is to calculate the bucket number. And so to do this, we take the hash code and then mod it by the number of buckets to get a valid index into our array. So once we know the index of our array, which is the specific bucket that that item corresponds to, we will insert it into that bucket. Any questions so far? All right, moving on. So runtime. So there are sort of 2 important operations of a hash table that we'll go over. So first one is contain. So we check whether some item is in a hash table. And so the best case is constant. So either maybe there's no items in that bucket or we find the item immediately. However big the hash table is, it's always going to be constant. And the worst case is theta n. So you can imagine there is a possibility that all of your items in the hash table are going to be in a single bucket. And in that case, it's going to potentially take n time to like go through that entire linked list. And then, yeah, so insert has the same best case and worst case. And so generally in hash tables, we don't allow duplicates. So we have to look through the entire linked list in a particular bucket. And if all the items are in one bucket, then looking through the entire linked list will be theta event. And yeah, so like for the runtime, like we sort of optimize it by having resizing, and resizing hash tables have an amortized runtime of theta 1, which is constant. And you can kind of think of it as like an average runtime. Like most of the time, it's going to be constant, but technically there is still that worst case where all the items end up in one bucket, which makes it really slow. But yeah, quick note about resizing. So we keep track of n over m, which is the number of items over the number of buckets, which is just the average number of items per bucket. And when it gets too big, we're going to resize. I think in this class, we usually resize by a factor of 2. So we multiply by 2. And then we redistribute all the items over the new buckets. And so one common question you might be asked is, what makes a hash code valid? Or like, is this a valid hash code? And there are 2 qualities that make a hash code valid, and they are determined that the hash code is deterministic and the hash code is consistent. And so a hash code being deterministic means that if we get the hash code of a particular object multiple times, it should return the same thing every time. And so if you see like a random number or like a time or something, like that's a sign that it might not be deterministic. It might return a different hash code on multiple calls, which makes it invalid. The second one is consistent. So if 2 objects equal each other through the equals method, then they must have the same hash code. So yeah, that's what being consistent means. Any questions about these 2? All right. Yeah, I'll skip over the good hash code part since that's a little bit less important and move on to the practice question. But yeah, so this is spring 24 midterm 2, I believe. And in this question, we're considering 2 hash codes and 2 equals methods. So the default hash code is the implementation of hash code provided by the object class. So this is just if 2 objects are like, they're the same instance, then they have the same hash code. Otherwise, they have different hash code. And the trivial hash code, it just always returns 0. For the equals method, the default equals method is if 2 objects are the same instance, they are equal. If they are not equal. And then for the trivial equals method, it just always returns true. And so I'll give you like a quick second to think about it. For A and B, there are 6 subparts for this question, but I'll give you a quick second and then we can look at it together. All right. Yeah, so for this problem, we don't really have to worry about whether or not it is deterministic because there's no randomness going on here, or anything that might be different over multiple calls to hash code. And so the thing we're going to have to think about here is consistency. If 2 objects are equal to each other, then they must return the same hash code in order for the hash code to be valid. And so yeah, so part A, the default hash code is a valid hash code for the trivial equals method. Yeah, any guesses as to which one this would be? False, yeah, and why do you say so?
Because the equals method is also going to return true, but we're going to have different hash codes for like different objects.
Yeah, exactly. And so the equals method always returns true for the trivial one, which means like it's possible for 2 objects to equal each other and have different hash codes, which makes the hash code invalid. Yeah, what about B? True. And why do you say true?
Then compile the hash code topic, so I think it's 0, so it's going to be the same object.
Yeah, exactly. And so the trivial equals method always says that 2 objects are equal. And so like if we think about consistency, that 2 objects which are equal must have the same hash code. And so if 2 objects have the same, or like it returns true for equals whatever object it is. So we will always be the case that 2 objects with the same hash code are equal because it's always the case that 2 objects are equal. Yes. Oh, when you have different objects and they're still all returning 0. So if there are different objects, like different instances, the trivial hash code will always return 0. So the hash code will be equal for those two different objects. And because the trivial equals method returns true, those two objects, even if they're different instances, the equals method will return true. And so it's satisfied that like two objects that like equal each other will be also have the same hash code. Yeah, good question. I think for the sake of time, I'll run through the last 4 really quickly. So the next 2 are the trivial hash code is a valid hash code for all equals methods, and the default hash code is a valid hash code for all equals methods. And so C is false, or sorry, C is true, because it's impossible for 2 objects to have a different hash code. So it's impossible for 2 objects with a different hash code to have, yeah, so like if we have the trivial hash code, then it'll always be the case that like 2 objects that equal each other will have the same hash code. And then for the default hash code is a valid hash code for all equals methods. This is false because in this scenario, it's possible that 2 objects will not equal each other, or sorry, 2 objects will equal each other, but have different hash codes simply because they're different instances. And for E and F, so E and F just say like the only valid hash code for both the default and trivial equals is like the default and trivial hash code. I won't go into too much detail so we can get to the next topic, but basically you can think of other possible hash codes that also satisfy the constraints. Yeah, do you want to take over? Yeah, I'm skipping that one. This is being weird. Oh no.
Do you want me to?
I think it's just being slow.
Yeah. If I just
It is really sad.
right. Hey, can everyone see my screen on the Zoom? I'm gonna. Okay, we're gonna go over Heaps. My name's Prisha, by the way. So Heaps, you guys have probably like, raise of hands, like how comfortable do we feel? Like good, medium, bad. Yeah, there's like a mixture, as there always is. Nice. Okay, so I'm gonna give like a brief overview of Heaps as like a data structure, and then we're gonna do one practice problem with it. Heaps are normally one of those things where once you understand like a min heap and then a max heap and like ordering there, there's not much more that they can really test you on, and there's not really like much more to be tested on. It's a data structure that takes in things and gives out things. But so just to recap, these are like by the way, the insert and deletion methods that I have on the slide are good to put on your cheat sheet. So heaps are complete binary search trees. And they're binary search trees because the per like the binary search properties, heaps dependent on like whether they're a min heap or a max heap, they follow a similar structure. Heaps specifically, there's normally like in a min heap, there is either the smallest element as the root or in a max heap, the largest element at the root. And we'll see that in a second in like a couple examples I have. Insertion into heaps, it's basically you always add to the lowest level in the earliest possible position. So the lowest level of that heap, you add to the leftmost opening that they have there. And then you bubble up or bubble, actually you wouldn't bubble down if you're adding to the lowest level. So you'd bubble up in accordance with like the property, the binary property of that heap that you're dealing with. So for example, if you're dealing with a min heap and you add a value that is smaller than its parent's value, then you're gonna bubble that value up. So where it like sort of switches positions with its parent, and you do that until the binary property of the child being a larger value than its parent is true. The best case runtime for this is O of 1, because let's say you add an element to the lowest level in the leftmost position, and it belongs there. It's a larger value than its parent value. then this is our best case scenario. You won't have to do any sort of bubbling. The worst case would be when we need to actually go all the way up and actually replace the root that we have currently. Let's say we insert like in a min heap the actual like a new smallest element. Then you'd have to bubble all the way up from the lowest level up to the top to the root. And this would be log of n because you would have to go through log of n levels to get to that top root node. N, by the way, in this case, is the number of nodes in our entire heap, or the number of values in our entire heap. This same logic can also be translated to a max heap and just like sort of flipping the language. Excuse me. To delete, we kind of do a similar thing. We take the rightmost node of the lowest level, so the most recently added node of the lowest level, and delete it and make it the root. So we switch the root with the rightmost node of the lowest level. By the way, in deletion, we only delete the root of a heap. It's a little bit like different than other types of trees where like in an LLRB, you can delete like one node like anywhere in the tree, but in a heap, we can only delete the root node. And so how that would happen is you would take your bottommost node or the most recently added node, and you would like replace our root node with that and then bubble down until all the binary properties are agreed upon again. The new root value in the can be valid in case of a heap of 2 or 3 items. And this would result in like a best case sort of scenario where like the runtime of this would be O of 1. So let's say we had like 2 or 3 elements in our heap, replacing our root node with one of the like element 2 or element 3. That wouldn't really do anything in terms of like that might not like cause us to have to bubble down because there's only like so many elements in our heap. And that would result in our best case runtime of O of 1. Otherwise, like similarly to inserting, we would have to go back if we're in the situation where we have to go all the way back down to as much as possible, like better in this heap structure, then we would have O of log n. And the child nodes, I want to make this a very like I want to point this out very distinctly. Child nodes of a particular node have no explicit relationship. So if I had like a parent node and it has 2 children, the only relationship that is sort of tying these 2 children together is the relationship that they have with the parent node. There is no actual relationship between the 2 children. Yes, go ahead. You have a question. Yes. So, okay, yeah, that's a great question because I think there's just like a lot of words on there that kind of get tossed around. We're actually the only node that we're really deleting is the root node, and you're correct about that. What we're sort of doing right now, I said delete it because the root node position, we're actually replacing that value with that value of that last this new node that we're bringing up. But it's correct to say that we're like really like the only node that we're fully deleting is the root node. Yes. Yes. Thank you for clarifying that. Do we have any other questions about any of that, by the way, before I move on to the next slide? Yeah, no.
So are there like just complete binary trees? They're not like associations.
Oh, okay. Yeah. There's a typo on the slides that we will fix very soon, but the first line where it says heaps are complete binary search trees, they're simply binary trees. They're not binary search trees. That's sort of a typo because binary search trees, they have that property where items to the left-hand side are, or items, I'm basing you guys. So the items to the right-hand side are greater than the parent node, and then items to the left-hand side are less than the parent node. And that's binary search trees, but heaps aren't binary search trees. They're only binary trees, and the binary tree property is that a node can have max 2 children. Yeah. Thank you for bringing that up, Andy. Okay. Any other questions? Cool. Slide. So this is specifically going over max and min heaps. And these are the 2 that you're going to deal with in 61B. They're very similar in sort of like the structure that they are visualized in, as well as like the array style that they're visualized in. The way that they differ is that max heaps, we always have our largest value at the top node, at our root node. While in mid heaps, we have the smallest item of like our heap at the root node. Child nodes are smaller or equal to the parent in a max heap. And then in the mid heap, child nodes are larger or equal to the parent. Also, this is a unique property where you can have equal to values in our heap structure, which is also visualized as tree, because I think like one key part of binary search trees is that you can't have repeated elements, but in heaps you can. So that's something else to be wary of. Do we have any other questions about this? Okay. And one last thing that I want to go over before we get into like a practice problem is heaps can be visualized as arrays, but when we do this visualization, the array is never 0 indexed. So the array is going to be 1 indexed when we're visualizing a heap, and the root is always at index 1. The remaining indices in the array are sort of in level order, or that BFS traversal that we did earlier in the review. What you can see that sort of over here in that example, where 16 is at index 1, and its two children, 14 and 10, are right after in their sort of level order like positioning. Also, the reason why we index at 1 instead of 0 is because, or we start our array really at 1 instead of 0, is because we want to do some like very unique like index algebra using properties that sort of dictate where the child nodes are of a particular node in comparison to the parent node. And that's sort of written on the slide right here. It's a great thing to put on your cheat sheet, but basically the left child node of a node at index x is always going to be at index 2x. And then the right child node of an index of the right child node of a node that's at index x is always going to be at index 2x plus 1. And this is true for any sort of index in the array. And then one key thing again to point out, this array is never going to be 0 indexed. There might be a conceptual, I can imagine there being like a conceptual question where, okay, imagine if this array was 0 indexed, what would these new properties be of this like array? And in that case, it would be 2x the left child would be at index 2x minus 1, and then the right child would be at index 2x. So it would just be a shift over. Yes, go ahead. No, that's a great question. So to repeat the question for those on Zoom, if we didn't have this part of the heap right here, or this and like I guess the visualization of a tree structure, would this be a valid heap? And the answer to that is no, because like when we're inserting elements into this heap, then the way that this would work is that we would check, okay, does like the way that we would insert, it would be, so insertion, going back to the previous slide, always add to the lowest level in the earliest possible position. So when we have a heap that's of like items 16 and 14, the next place that we can add the item is going to be on the right-hand side of 16. Because that would be the earliest possible leftmost position of the lowest level then. So in a heap, just to reiterate, it fills in like all the way through, like line by line. Great question. Yeah, so to repeat that, at index, if we were in an index, a 0 indexed array, the left child would be at index value 2x minus 1, and then the right child would be at index 2x. So basically what we would be doing in that array is just shifting everything over by 1. Great question. Anything else?
For example,
No, go ahead.
that makes sense.
Okay, great, perfect. Anything else? Okay. So I'm gonna give you guys some time right now. I'll give you guys like 3 minutes to work on this problem right here. Just to go over, this is basically a min heap taken from spring 2018 midterm 2. And it's asking you to figure out a couple different parts of this heap, like the smallest value, the largest value, and the median value. I want to note it's asking for the median value and not the mean value. And also to note that assume that the values are inserted into the heap in increasing order. And what that means is there's sort of, when you're inserting things in increasing order, it means that like H is inserted and H is the smallest, and then D is inserted and D is the second smallest, and then L is inserted and it's third smallest. So it's going like smallest to greatest, and that's how we're inserting. Yeah. So take like 2 more minutes to work on. Huh? No, it's cool. So do you want me to repeat what I So the values like H, D, L, those are just like, think of those as variables. That's not like the actual value in the heap. What it means when things are inserted in increasing order, it's a good clarification to ask about because I think it makes this problem very unique. So when things are inserted in increasing order, so remembering back to how we insert things, we always add it to the next opening in the heap, right? Like the leftmost exactly on the lowest level. Yeah. And so what that means is when we're inserting like that, the smallest items are inserted first, and then the next item that you're going to insert is going to be bigger than the smallest item. Or sorry, bigger than the previously inserted item. So I'm going to give away part of this question really quickly. Property of a min heap, the smallest item is always going to be the root node. So the root node, yes. So H would be, by the way, that's part 1 of part A. H is going to be our smallest value. Yes. Yeah. Okay, sorry about that. Take about 1 more minute to work through median and largest value. All right, I'm gonna ask you guys to finish up any last thoughts and just look up whenever you're ready. Cool. All right, I'm gonna start going over part A now. So we just sort of going over min heap again. Min heap smallest value always has to be our root node. So the smallest value is going to be H. Median value is a little bit more tricky. And I think an important thing to understand about the median of a heap, it's the median of any sort of like set of integers, it's always the middle value. It's never like the average value. That's mean. And the middle value, since we know that we're inserting things into the heap in increasing order, that these are going to be ordered elements. And what that means is, so our heap is of size 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 items in our heap. So going through these in sort of like the level order traversal of this tree-like structure, we would need to find the middlemost item or the 6th item in our heap. And so when we do that, it would be HDL, so that's 3, 4, 5, 6. So K is going to be our median item because we're inserting in increasing order, and it is the 6th most item in our heap for that reason. Does that make sense to everyone? Okay. And then largest value. So this is kind of a tricky part of this question because you may think in like a normal heap when you're sort of inserting kind of randomly, it could be like the largest items could really be anything that's a leaf node. But since we know that we're inserting an increasing order, that our largest item is actually going to be the last item that we've inserted, or whatever that bubbles up with. And the last item that we've inserted or like bubbled up, or like sort of like bubbled up with is G. And so since G is the last, so we see G over here on like the furthest part of our bottom layer, we know that that's going to be our like largest element technically in this min heap. And so for that reason, G is going to be our largest value. Do we have any questions about that? Okay. There is another part of this question. So this is the question, right? Part of the second part of the question that we're gonna go over. This is like really like testing like how if you know like how ordering matters to insertion. So excuse me. Part B, assuming values are inserted into the heap in decreasing order, indicate all the letters that could represent the following. So simply we're doing the smallest value. I'm gonna give you guys like a minute to do that as well as C, just because for time's sake. C is assuming all the values are inserted into the heap in an unknown order, indicate all the letters which could represent the following values. Take a couple minutes to look at that, and then we'll go over it in like 2. Also, I'm going to move it back. So this is like the heap for anyone that needs that reference. Take about 1 more minute. Sorry to rush everyone. Okay, we're gonna start going over this problem now. Oh, shoot. Okay, so our first question is, assuming all the values are inserted into the heap in a decreasing order, indicate all the letters which could represent the following value, which is the smallest value. Does anyone want to take a guess at this that's in the room right now? Also online, if you want to do it over Zoom. Yes, in the back. Yeah, exactly. What's your name, by the way? Okay, thank you, Joshua. Yeah, so that's the correct answer. So for part B, the smallest value is going to be H, regardless of the order that we pass things into it, because the smallest value of a min heap will always be at the root of that heap. Great job. Okay, so then in part C, now we're assuming all the values are inserted into the heap in an unknown order. Indicate all the letters which could represent the following values, the median value, and the largest value. So just to go back over here, this is what our heap looks like. Do we have, I think, median value is a harder question than the largest value, but do we have any like guesses on what the like median value could be if there's an unknown ordering? Yeah, go ahead. DLBF. Okay, that's an option. Does anyone have another like guess at what it could be? That's like partially true, by the way. So it's actually, so it's going to be everything except for D and L. And the reason for that is we know that, so for our median value, we know that it has to have at least, actually, sorry, let me check. Everything except for D and H, my bad. So for the median value, all we know about our median value is that it has to have 6 elements that are possibly bigger than it. And, or I'm sorry, 5 elements that are smaller than it or 5 elements that are bigger than it. And so when we look at our values over here, H1, we know H is the smallest element. So that can't be our median value since we know it's going to be the smallest. D, on the other hand, so when we're counting like how many elements are bigger or smaller than all of the other elements, all we can say about L, K, and M, since there's nothing underneath them, and since we know that no children have a relationship to other children of like a given parent, L, K, and M can all be valid median values of the array, since we don't actually know what all the values of the array are. But also there is a possibility that there are 5 elements that in this heap that are larger than them, or 5 elements that are smaller than them. It's still a possibility. All we know is that the relationship between H and L and M, and L and K. We don't know what the relationship is to the other subtree of H altogether. And so for that reason, we don't actually know if like it is like if any of these are the median or not the median. So that still makes them possible medians. Does that make sense to everyone? Yes, go ahead. Yeah, okay. So I think like the best way to understand medians is to understand how many elements have to be greater than this value and how many elements have to be less than this value. There are 11 elements in this heap altogether. And if we're inserting in a random value, or sorry, inserting in a random order, we don't actually have any indication of whether D is greater than L or L is greater than D. We have no indication of that. So all we can really go off of is if we're going in a unknown order, then we simply need to figure out what elements could possibly have 5 elements that are less than them or 5 elements that are greater, if that makes sense. Okay, so what we know right now is like we have to have 5 elements that are greater and 5 elements that are less than. We know for a fact that H has 10 elements that are greater than it because it's their root value. So H cannot be the median value. The next thing is we know when looking at all of the other me personally, when I'm working through this problem, I look at how many elements are larger than whatever element that I'm working on currently. If it's more than 5, then I say, okay, like this can't be our median value. So when I'm looking at this, L, I know that K and M are greater than L. I don't know if anything in D's subtree is greater than L, since there is no relationship between the 2 children of a parent node. So we don't know B, F, A, C, E, G, or even D is greater than L. So we know L has 2 items that are greater than it. That still technically fits our possibility for a median because we don't like, it could be 5, but we know for certain 2. Same idea with K and M and any of the leaves. We know for a fact that like there are like, we know that they don't themselves have any children that are greater than them, but we also know that like we know K is greater than L and we know M is greater than L. We also know that A, C, E, G, or M could all be larger than K. We also know that K, A, C, E, G could be greater than M. So for that reason, L, K, M can't be median values. Then going into the other subtree, D has 6 elements that are greater than it. So we know for a fact that this can't be a median. Then going into B, F, A, C, E, G, similar as before, there can be 5 elements that are greater than it. There also is a possibility that there isn't, but there's still possible to all be like there is like 5 elements that are greater. Does that make sense? Okay. And then the last question is the largest value. So do we have any like people, does anyone have like a guess at this or any idea about that? Any of the leaves? Okay. Do we have anyone that has a different answer than that? Okay, great, because that's correct. Any of the leaves could be the greatest value in this heap. And the reason for that is that we know that any node that doesn't have any leaves, or any node that has leaves, it can't be the greatest element because there is an element that is greater than it already. So for example, D and L, they can't be the greatest elements because we already know that since this is a min heap, B, F, K, and M for their respective parents are already greater than their parents. Yeah. Does that, yes, question? So yeah, that's a great question. I think like the unordered part, it's like you should assume that when you're inserting into a heap, it's always unordered. It's only for the previous parts of this problem, it specified that it was either or like inserted in an increasing or a decreasing order. And when things are inserted in an increasing order, you know that it fills in into a min heap, like basically in a level order way. So it goes F and then DL, and then we know that D is less than L in that situation. Similarly, if we insert it in an increasing way, it would kind of be flipped. Does that make sense? So for like the unsorted, I think like for the largest value, it's any node that's a leaf. That's like sort of like the go-to, like if any node that's a leaf, it could be the largest value. And for the median, it's any node that could have that could have like, like half of the nodes be bigger than it. Half of the amount of nodes be bigger than it. Yeah, great question. Any other questions on heaps? Doesn't seem so. That was actually our last question on heaps. Thank you guys for coming out today. Good luck on the midterm. You guys are all gonna do great. And also, I want to make a note. CSM, we're not affiliated with core staff in any way. We should have done this at the beginning, but not affiliated with core staff in any way, even though some people might be on core staff, some people may not. But if you guys have any questions, feel free to thread up in like our CSM post, I think, or I think Matthew's email's on there. So he can also like direct questions back to us if like something you're confused about a specific topic or one of the problems or explanations that we did. But yeah.
Be in the post, so yeah, feel free to email me and we'll get back to you. Anything like, oh, this didn't make sense, or can I see a problem like this, or what if I just edge case? Yeah. Great.
Yeah. Thank you guys all for coming. Have a great rest of your weekend, and like midterms are hard, but you're like they're just exams. So yeah, thanks for coming. Oh wait, I should pause the recording.